Okay, we're gonna wrap up chapter 3 today, and I want to introduce op amps. Well, at least a few slides of introduction of the op amps. So wrapping up chapter 3, there's just a small homework on voltage and current division. So I just want to quickly go over those problems. Let's think. Let's see, 113, chapter 3. All right. So that should be homework 808, problem 3.12. I think problem asks to determine the value of RL, I believe, for a particular voltage. So it gives you the no load voltage, or asks you to find the no load voltage. I don't have the questions in front of me, but RL is not connected. No load means RL is not connected. So if RL is not connected, then the 100 ohm and R2 form a voltage divider network. So you can find the voltage VO from voltage division. Apply voltage division. Again, there's a specific purpose to this homework, right? You can solve this by by finding the current and then applying Ohm's law to determine the output voltage. But the point is that students need to be familiar with the voltage division and current division techniques. So you need to familiarize yourself with that and use that analysis technique, because that is something I will also ask on the final exam. Right? We are required to teach you certain topics and then required to assess your knowledge of those topics. So voltage division and current division. Do not skip. So you find VO from voltage division. Then you connect RL. And now they're asking you to find either the value of RL or trying to find VO again. So when you connect RL, now RL is in parallel with R2. So RL becomes parallel with R2. You reduce that to find Req of those two resistors. Let's call it R3. And now the 100 ohm resistor and R3 are in series. And you can recalculate again using voltage division principle and solve for the voltage VO or solve for the resistance RL. Okay. Does that make sense? Hopefully. You can review the video later if you need help. Again, this is just a quick step guide. Homework is meant for students to learn by themselves, but I just want to provide certain hints on the steps. Okay, next one is 3.13. Again, it's a question about voltage division. This one requires some thinking about the fundamentals of voltage measurements. So you have a 30-volt source. You have a series connection of 3 resistors, R1, R2, and R3. Okay. The terminals V1, V2, and V3 are shown does not mean anything is connected there. We are simply measuring a voltage. Okay. If you're measuring a voltage at those terminals, nothing is connected. Those resistors are still in series. So the question being asked is, determine R1, R2, and R3 for specific values of V1, V2, and V3. Okay. I think V1, I believe, is plus 15. V2 is plus 5. And V3 is minus 15. So what does it mean? You have 3 resistors. This is common, so it's 0 volts. That's your reference. In the lab, if you're taking measurements, the common terminal is where you would connect the negative end or the common terminal of the multimeter. That's all it means, nothing else. And then you would take the red terminal and you would connect it to V1, then you connect to V2, and then you connect to V3 to take the measurements. So this is 0 volts. This is plus 5 volts, meaning this is 5 volts above 0. And this is 15. So it's 15 volts above 0. And this is minus 15. So 15 volts below 0. That's all it means. It doesn't mean anything else. All other rules like Ohm's law, KVL, KCL, they still apply. Yeah, they apply as it is. Current direction does not change. Voltage polarity would change depending on the point of reference. So the way you would want to solve this is you find the ratio of the resistors and you add them up. So you have, this is your common terminal, right? So you can see the resistance value would be in proportion to the voltage drops. If you look at the voltage drop, they are a multiple of 5 volts. Does that make sense? And there are multiple. So you assume a value for this resistor as R, and then you can find this as X times R. This would be Y times R. X and Y are constants, right, depending on the proportion. And then you write the voltage division expression for these resistors, for each resistor. Okay, for each resistor. Again, if you already solved this, or if you already know of a method, if you are comfortable using that method, you can use that. But voltage division should be a part of that method. Okay. If you get stuck, you can refer to these steps. That's how you would solve this one. Any questions? Okay. This one's current division. This isn't too bad. I think it's a straightforward question. It asks you to find the current through one of the resistors, so you simply apply current division. There's not much to this. Simple current division application. The next one, however, requires a little bit of thinking. It's just a few additional steps. Again, not much. Sorry, not this one. This one also straightforward application of current division. So I believe 3.19 and 3.21 are straightforward. And then 3.23, that requires a little bit of thinking. So it asks you to find the the current through 10 kilo ohm resistance first. So if you want to do that, we have to reduce everything to the right of the current source to one single REQ. Okay, so you would have to reduce this to one single resistance. Then you should have something like this, 10 kilo ohm. And then this would be, I don't know, 1, 2, 3, 4, 5, 6, let's say 7. You find the REQ for this one, and then you can apply current division. Okay, apply current division. Again, we have to reduce everything to a parallel network. Okay, in order to do that, we need to find REQ, reduce everything to the right, one single resistance. And once you have that, then it asks you to find the current in, can't remember for sure which one. I believe it asks you for this current, the 5 kilo ohm current. Or maybe it's this one. Okay, then all you have to do is the current source minus the 10K current. That gives you the total current going to the right side of the circuit. And then you apply current division again. Okay. So again, start working on it. If you get stuck, you can review this video. And then if you're still stuck, just send me an email, reach out to me, and I'll be happy to help out with your questions. Okay. All right. So that is the end of chapter 3. That is the end of chapter 3. Let's bring up chapter 4. Okay. Well, actually, it's chapter 5 in the book. The reason we are covering this earlier is because the lab requires students to use the op-amp. So we want to cover what op-amps are. Okay. Anybody familiar with op-amps? Operational amplifier? Okay. Highly versatile circuits. These are available as a microchip you can purchase off the shelf. This is an off-the-shelf component. The name is operational amplifier. Okay. They are integrated circuits. They are microchips comprising of transistors, diode, capacitors, and resistors. And there are hundreds of varieties of op-amps that are widely available in the market. Okay, you simply buy an op-amp off the shelf. Now, the words transistors, diodes, they're all not familiar to you. You're going to study that in EE 306. Okay, that's like a year away from now. But students need to know how to approach the op-amp as an off-the-shelf component. So typically all circuits classes, no matter where you take them in the world, you study op-amps in your first circuit class. I did it when I was a student. My professors did it when they were students. Okay. And you are doing it now. And then I think 20 years later, students following you would be doing the same thing. So we are not going to go inside the circuit, but what we want to look at is the terminal behavior. Okay, terminal behavior. We are going to use the op-amp as an off-the-shelf part. It has some terminals, the external. So we're going to analyze the external circuitry, not the internal. Okay, it's a sealed box to us. We don't know what's inside. We don't actually care what's inside. We don't know how the components are going to behave inside the circuit. We don't really care. We're only interested in the terminal behavior, only in the external analysis. And that's going to be our approach. Okay. Now, the reason they're called operational amplifiers is because we use them to implement various mathematical functions. Mathematical functions such as integration, differentiation, addition, subtraction. There is amplification, filtering. All sorts of applications can be implemented using op-amps or operational amplifiers. Short-term acronym is op-amp. Full form is operational amplifier. Okay, operational amplifier. One of the most common ones is the IC MU-A741. And that's probably what's in your lab kit, 741. This is the exact same chip I used when I was a student. That's more than 35 years ago. That's still, even before I was a student, long time ago, before I came along. 741 was introduced in the 1960s by Fairchild Semiconductor and still the gold standard today. When students first begin their journey as an electrical engineer, 741 is the go-to chip. And then as you go in higher classes, you're going to learn about other op-amp chips, and you'll use other op-amp chips for a variety of applications. So the internal circuitry, again, as I said, we don't really care what it is inside, but I just like to show, what that looks like. Considering the complexity of devices nowadays on a single integrated circuit, you have billions and billions of transistors. This is pretty much nothing. Okay, it's just a few handful of transistors, one single diode, capacitor, and a few resistors, and that's it. Not much. One thing you should know is that these are configured as a differential amplifier. Okay, that's the most fundamental connection inside an op-amp. It's a difference amplifier, meaning it amplifies the difference between two input signals. Okay, so this configuration is known as a differential amplifier. And again, this is something you'll study in like 307. So you'll study the basic fundamentals in 306. and then you'll study higher level circuits in 307. All right, IC 741 is an 8-pin, comes in an 8-pin package. So one single op amp. ICs, if you don't know, are always standard. So the pinout configuration for any IC, I don't know why I did it this way. Okay, rectangular chip, black epoxy packaging, right? We don't want it getting affected by any external light sources or any external energy. And there is a notch at one end or a dot. Okay, what does the dot or the notch indicate? For those of you who have used it in the lab, pin number 1. So the notch indicates pin number 1. Always. Doesn't matter what kind of IC it is, doesn't matter what kind of chip it is, doesn't matter who manufactures it, doesn't matter the number of pins, whether it's 8-pin, 14-pin, 16-pin, 20-pin, 48, 100-pin chip, doesn't matter. That's standard configuration. Always start with pin number 1 on the left. So if you have this chip, you have an unknown IC in your hand, you're trying to figure out the pin out, you hold it like this in front of your face, notch at the top, pin number 1 is to the left of that notch. And then you start counting down in this direction, make a U-turn, and you go up. And that's the last pin right there. That's the last pin. Again, whether it's 8-pin, 14-pin, 16-pin, 20-pin, 48, 100-pin IC, doesn't really matter. The pin out configuration is always like this. Start from the left, go down, make a U-turn, and then go up. So in the 741, the chips, doesn't matter who manufactures this, the pin out for a 741 is standard. Okay, there are multiple manufacturers all across the world who make and sell these. The pin out remains the same. Okay, so anybody who has a license to create this op amp chip, pin out remains the same, and that's what you have in your lab kit. So let's look at the terminals. Okay, you have an inverting input and you have a non-inverting input, pin number 2 and 3. Those are the two most important ones. Those are the inputs for that differential amplifier. The op amp's property is that will amplify the difference between those two input pins. Okay, so input signals are going into those pins, pin number 2 and 3. Output is taken from pin number 6. That's what it's shown in the configuration right here. Okay. Now, so an op amp will always have 3. Symbol for an op amp is a triangle. It's a triangle like this. The triangle is also used for many other devices. Triangle is used for a diode. A diode has a straight line at the arrowhead. It's also used for a buffer. So a triangle is also used for a buffer. It's a buffer amplifier. Typically, there's a size difference. So a diode could be about this size. Buffer could be slightly bigger than that. And an op amp would be slightly bigger than that. Okay. So it could be a diode, buffer. It's also used for an inverter or NOT gate. So sometimes it could get confusing. But again, as an engineer, electrical engineer specifically, it is your job, not your job, but it's part of your skill set to be able to recognize what the circuit is. So again, op amp is a triangle. You have the inverting and the non-inverting inputs on the left. Typically, that's how an op amp would always be drawn. Input on the left, like any other circuit. You have the output on the right coming out from the arrowhead. And then you have two power supply lines, power rails, positive and negative. This is used to allow a alternating sine wave or square wave to go in its full swing, meaning something like this. Like a sine wave or an AC would have a positive peak and a negative peak. So these are known as dual supply lines or dual power supply lines. And it basically configuration looks like this in any circuit. Many circuits, if you see, this V plus and V minus may not be shown. It is implied that they are present. Okay, so sometimes they are implied, may not always be shown. Also, if you have a portable circuit, you don't have a dual power supply, then the negative terminal is connected to ground or the common or the negative end of the battery. So in that case, you only have a single supply. Okay, if you have a single supply, that's how it's connected. Okay, so there's a reading assignment for the op amps. Please go ahead and, do I have it? I think I do. If it's not online, then I'll make it available online soon enough. But there's a reading assignment, chapter 5. Please get started in homework, then get started on the op amp. Okay. All right. We'll end class here today, and we'll pick up here again on Wednesday. By the way, GPT beginning today using your Cal Poly email ID.